Unit 4, Section 13.2 Worked Examples. The graph shown has at least one Euler path. Use the graph to answer the questions below. Determine an Euler path that begins with vertex A. A partial path has been provided. Complete the path so that it is a Euler path. Remember what Euler's theorem tells us. And if we look at this graph here, we notice that it has two odd vertices. And so that tells us that this will have at least one Euler path, but no Euler circuits. The Euler path must begin at one of the odd vertices and end at the other one. And they're choosing in this example to have a start at vertex A. And let's go ahead and trace the partial path that they've given us and see if we can finish the last two pieces of it. So it started at A, and then it went to C. And then from C it went to D. And then from D it went to B. And from B it went to E, and then from E it went to D. And so where does it have to go to finish up? Okay, it can't go back to B because we've already been across that, so it's going to have to go to A and then to B. And notice that it's ending at the other odd vertice. Determine an Euler path that begins with vertex B. Type the vertices to complete the Euler path. And again, they've started and given us a partial path here. And you notice in the diagram, the partial path they've shown us is the dashed line. So we're now at point B, and we want to determine where we're going to go from here. So from point B, I'm going to have to go back to A because go on to A. I'm going to go over to A. And then let's go ahead and go up to E. And then from E, I'm going to go around to D. And from D, I'm going to go back up to A. And then I notice I can go ahead and finish on the interior here by going across to B, and then finally to C, and then lastly down to D. And again, notice that I end at one of the odd vertices. So let me go ahead and write this in here. So it went A, E, D, A, B, C, and then D. Determine an Euler circuit that begins and ends with vertex B in the figure. Now remember, a circuit must begin and end with the same vertex. So when I look at the answers here, I can right away eliminate answer D because it doesn't begin and end with the same vertex. And again, if we look at this, we notice that what does this have here? Let's take a look. Vertex B is even, vertex D is even, A is even, F is 1, 2, 3, 4 even. They're all even vertices. So if it has no odd vertices, there's at least one Euler path, which is also an Euler circuit. It can start at any vertex and end at the same vertex. So let's take a look at the possible answers they've given us and see which one makes sense. So let's start with the first one. And it tells us we're going to start at B, and we're going to go to B to D, and then from D to F, and from F to E, and from E to D, and from D to A, and from A to F, and then to C, and then to D. But I can't go from C to D because there's no connection there, so I can eliminate answer A. I'm going to go ahead and erase what I put onto my figure so I can try another circuit. And let's try the second one. Again, we're beginning at B, and we're going to go D, and then we're going to go to F, and then we're going to go to E, and then we're going to go to D and A, back to F, C, E, and B. And so this looks like the right answer, but before I decide that for sure, I'm just going to double check that C is not a correct answer. So let's try circuit C and see what happens when we try that one. And this one goes BD, FE, and then it's gone from E to A, which is not possible because there's not an edge between E and A, so it can't be C. So the answer has to be B. So the correct answer on this one is choice B. The layout of a city with land masses and bridges is shown below. Complete parts A and B. Is it possible for the city residents to walk across all of the bridges shown without crossing the same bridge twice? So I went ahead and I made a graph to illustrate the city. And there's islands A and C, and then banks B and D, and we notice there's some connections here. Island C is connected to bank B with 2 edges. And remember our theorem here, Euler's theorem, and let's take a look at what kind of vertices we have. So A is odd, B is also odd, C is even, and D is even. So I've got 2 odd vertices. So a graph with exactly 2 odd vertices has at least one Euler path, but no Euler circuits. And the path will begin at one of the odd vertices and will end at the other one. So it is possible. So the answer here is going to be yes. There is an Euler path that we can find. And remember, we have to start at one of the odd vertices and end at the other one. So look at the answers and the possibilities here. So we either have to start at A or B. And the only answers here that would be correct would be choice B says start at B, but it would end at C, but C is not an odd vertex, so that can't be the correct answer. So the correct answer is going to be C, because you have to start at one odd vertex and end at the other odd vertex. Use Flory's algorithm to find an Euler circuit. All right, so they've given me 4 choices here, and let's go ahead and try these out and see which one might be the correct one. And they're all starting at H and ending at H, which means they're circuits. So let's try the first one. So it goes HB, and then it goes to D. And this is going to get me in trouble because it's going to take me back to H, and I'm going to have to go back over H, and then it's going to go to C, which is not possible. So it can't be answer A. I'm going to go ahead and erase what I did there and try one of the other possibilities. Let's try B. So this one goes HD, BF, E. Okay, I can't go from F to E because there is no edge there, so it can't be B. Let's try C. HC, H and C are not connected. There's no edge there, so I can't be that one. Let's check the last one to make sure that's the correct answer. H to D, to B to F, to A to E, to G, to A to C, to B to H, and that's the correct answer.